Okay, sorry about the delay. So let's get started. Good evening. I welcome the viewers to this problem solving and live interaction session for the subject strength of materials offered by Professor K. Ramesh on the Swayam portal. So today we will be discussing the contents of week 2. So, so before we begin, are there any questions? Uh,
Sir, I was actually say that I am joining this session 28th May.
okay,
Okay, sir.
okay,
Previous session I am not attending it.
no problem.
Sir, that assignment are not submitted, sir.
No problem. Assignment date is actually till next week, so you can still submit it. Not a problem.
Okay, sir.
And also the
Okay, sir.
previous recording, previous week recording that is already uploaded and it is available on the portal. So that also you can watch at your convenience. Okay.
Sir, can you provide me my email ID, sir?
Uh,
Previous session videos.
no, you can log on to Swayam portal. From there you can see
Okay,
it. Okay.
okay, sir.
Or what you do on the screen where I'm presenting now, on
Yes,
the
sir.
screen on the left side you see this QR code, right?
Yes, sir. I am not visible, sir.
No, my screen you can see, right? It says strength of
Yes,
material
sir.
size.
Yes, sir. Yes, sir.
Yeah, ये जो लेफ्ट में जो QR कोड है आप इसको स्कैन कर लीजिए. It will take you to a YouTube channel where that video is uploaded for week 1.
Okay, sir.
Okay?
Okay, sir.
Okay, great.
Thank you, sir.
All right, thank you. Okay, so I think we'll start. So I'll just introduce myself for those who didn't join the last session. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras. I'm being guided by Professor K. Ramesh and Professor U. Saravanan from the Civil Engineering Department. So today we will be discussing the contents of week 2. So let us get started with that.
So before we begin, I'll just give a brief on how to label stress at a point. Basically, in the last session, we simply saw stress as a number, something like P by A or F by A or something. Whereas there are certain conventions to be followed. For example, let us take that there is a body which is subjected to some loads. And let us take one point. So this point, we will blow it up like that and represent it as a cube. The cube still has 0 dimensions. We are just looking at that point. So I have taken it like this. Let the positive coordinate axis be like that, x, y, and z. So we can see that this is the positive x face because its surface normal is pointing in the positive x direction. Similarly, we have the positive y face and positive z face here. So we will be labeling normal stresses like that. And we have shear acting like that for one direction, and for the other we will have shear acting like that. Since this is a cube of 0 dimensions, it doesn't matter where I show it, so I'll just offset it a little bit and show, and then we have it like that. So basically I have this as sigma x, since this is the x phase and the force is acting in the x direction. Similarly, this is sigma y phase acting in the y direction. This is sigma z phase acting in the z direction. I'll get this out of the way. Similarly, this is sigma or tau as we represent shear stress, tau acting on the x phase in the y direction. This is tau acting on the y phase in the x direction, and this is tau acting on the z phase in the y direction. This will be tau acting on the x phase in the z direction. This is tau acting on y phase in z direction, and this one is tau acting on the z phase in the x direction, and so on. So we have labeled it for the uh, positive phases. Similarly, for the negative phases, everything that will point in the negative direction as per this coordinate axis, whatever will point in the negative direction as per this coordinate axis will be taken to be positive stress. So generally we will be representing it like this. In two dimensions, it will water down to a square rather. So here we will be seeing this is sigma x x, and then this is sigma y y. It need not be tensile always. I'm just representing it like this. And then this will be a positive shear stress. This is tau x y. Similarly, I have this as tau y x, and so on. So there is something interesting about this. I'll just make a copy of this. I'll take it here. Let me remove the normal stresses for now. So I have this as tau y x. So under the action of these two alone, under the action of tau xy alone, the element, if left to itself, will try to rotate like that. But since this is in equilibrium, there has to be an equal and opposite couple generated like that, which is why on the y phase we will have stress generated like that, so that it counteracts this. So if this is tau xy, this is tau y x. So from moment equilibrium, we have tau xy is equal to tau yx. So this is known as the equality of cross shears. This can happen cyclically for every plane there is, that is tau xy we saw and tau yx we saw. Similarly, tau xz and zx, yz and zy. So this is how we represent stress at a point in 3 and in 2 dimensions and employing the equality of cross shear. So this is basically called the equality of cross shears. So with this preamble, let us look at the questions that were solved in the session.
So now let us look at this question. Consider Tn as the resultant stress vector at a point on a plane whose outward normal is n. So now what I have done, I have taken one object which is stressed again as usual, and then I have taken this point, and at this point, now at this point I can cut this body like so, like that, or I could cut this body like that through that very point. So when it comes to a point, there are infinitely many planes passing through that point. What I'll do is, I'll take this body, let that be the plane, and I have cut the body at that point along this plane. So I have exposed it like this. So once this is exposed, I have a normal vector, normal, surface normal to that, which is denoted by n cap. Cap because it is a unit vector. I just want to represent that direction, which is defined by that n. Okay, is passing through that point. Choose the correct relations to evaluate the resultant stress vector at this point. Sigma n represents the normal stress, tau n represents the shear stress, and tau xy txyz represent the traction vector components along the positive xyz coordinate system.
So before that, let us see what the stress vector basically is and why we need it. So this stress vector is also known as traction vector. So it is basically a vector whose components are stresses. And why we need it? So in the experiment conducted in the lectures, we will see that if we have a chalk piece and we were to pull it like that, we see that it fails like this. Whereas if I were to take the same chalk and instead we apply a twist instead of a pull, so in such a case, it happens to fail like this. So even if I were to take one point, for the same point, the response is different based on how I apply the load. Hence, it becomes important for me not only to analyze stress at a point, but also along the infinitely many planes that pass through that point. This is why this is where the concept of stress vector comes in handy. So, for example, if I were to take the same diagram and let us say that the traction vector here is like that. So how we represent traction vector is by capital T or small t or whatever that is. And on the top, we mention the plane on which this is acting. So presently we are looking at the n plane, which has the unit normal as n cap. So here we will be writing n. So this is the traction vector at this point. Now we can see that we have our coordinate system like that. So this is x, y, z. So since this is a vector, we know that we can resolve this vector. For the moment, I am removing this n cap. We know that we can resolve this vector into three components. So this is along x, this is along y, and let us hypothesize that this is along z. So these blue ones are nothing but the components of the original this traction vectors components along the x, y, and z direction. So how do we represent this? So this is the same n t along n, but in the x direction, the x component of that. Similarly, this is t n along the y direction, and this is t n resolved along the z direction. So this is one way to decompose the traction vector into its components along the xyz coordinate system. Now let us say that I were to take the same thing again. I take the same diagram, but instead of resolving it along the xyz, I instead decide to resolve it along the normal and tangential directions to that plane. Now, now what is the normal direction? I know that this is the normal direction to that plane. Let me just remove this for once. However, I know this is my normal direction. So if I were to resolve the same traction vector or the stress vector along the normal direction, so it will have a component like that. And then along the tangential direction, it will have a component like that. So this normal component Tn, we saw that this is Tn and the component is acting along. Here we saw the component acting along x had a subscript x. So here it will have a subscript n. I hope that is clear. So this is also known as sigma n, which represents the normal stress on plane n. Similarly, this would have to be Tn, but this is along a direction that is perpendicular to n. So essentially, this would have to be n plus pi by 2, so to speak. But we won't get into so much of complication with our symbolism. We simply label this as tau. That is, tau represents the shear stress. So this will be represented as tau along n. So with these two discussions, here we have resolved Tn into the three Cartesian coordinates bases, basically x, y, and z. So from this diagram, we can conclude that Tn, the square of the magnitude of Tn, is nothing but the sum of the square of its components. So the components being Tnx squared plus Tny squared plus Tnz squared. So this is one result we have got from decomposing our stress vector along the xyz coordinate system. While the same vector I can decompose into the normal and tangential components. So from here it follows that the magnitude of Tn is nothing but sigma n squared plus tau n squared. So this is another result we have got. So what we have done, we have resolved the same traction vector into two different directions and have just expressed them as the sum of the square of the components. So with this, let us look at the question again. So which are the appropriate options? We can see that option 1 is correct. Option 2 basically has x, y, and then the normal stress added, so that is not correct. Option 3 has sigma n squared plus tau n squared, so that is correct. As we saw in the second representations, we can see that why the rest of the options are not correct. So I hope this is clear. It's just a brief about why we need traction vector. For at one point, we need to analyze the stress in all the infinite planes possible. So for any plane, how it is represented is what we saw. Now the issue is at every point, if we have to study the traction vector or the stress vector at every conceivable plane, it becomes very problematic. So that is where the stress tensor comes to our rescue. So let us see what the stress tensor is using the same example. Now let me take that same body and let me just keep it here. And also let me take the coordinate system from here. So I have the coordinate system. Now if I take the body and I cut it such that it exposes the first cut exposes the x plane, the second cut exposes the y plane, and let the third cut be, because it is out of the plane of the paper, let us consider that this itself is the third cut. Let us consider that this itself is the third cut, which has exposed the z plane. Now let us take that the traction is like this along this cut, which will be represented by t of x. This is the vector. On the y plane, because this is exposed, this will no longer be there. So on the y plane, let us say that the traction is like this. So this is t of y. Let this be some generic direction again, t of z. Now we saw that we can resolve this traction into the three. We can resolve the traction or stress vectors into their x, y, and z components. So if we do that, so for the first case, we can resolve this vector into three components. We can resolve this vector into three components. Similarly, this into three components. So how will that look? So the first vector t x can be resolved as t x along x, t of x along y, t of x along z. Similarly, t of y can be resolved like t of y along x, t of y along y, t of y along z. And cyclically, I can take it how it will look for z also. So for the z plane, it will look like this. So I take it that that is clear. Now, what the stress tensor is? Stress tensor at this point of interest. So we have all cut this at one single point, which is this one. So at that point of interest, the stress tensor is nothing but represented by sigma, which is nothing but a collection of these traction vectors along the xyz. So it is this, and then I put this on its side, and then I put this on its side. So this is essentially my stress tensor. Now, in our earlier discussion, we saw that when I have the same subscript, I will replace it with a normal stress. When I have n and n plus pi by 2, which I did not write, it will be tau. So, applying the same convention here, my stress tensor can actually be written at this point like this. So, it will be Txx is nothing but sigma x x. Tyx is nothing but tau y x. This will be tau z x. So this is my stress tensor. Now we will see how this comes in handy for finding out the traction vector on any plane for the same example as discussed in the session.
So we have the coordinate system as such. So we have x, we have y, and we have z. So at this point, if I were to say that the stress tensor is basically sigma x x, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, and then sigma zx, sigma zy, sigma zz. For the sake of this question, basically this is the stress tensor at that point. Now if I want to get the traction vector at this point, now what I'll do, this n can be represented as, this n is a vector, n is a vector which can be represented by three components, nx, ny, and nz. So any vector can be written as nx I cap plus ny j cap plus nz k cap. Now for ease of multiplication, what we will do, we will represent the same thing as a column vector, nx, ny, NZ. So what Cauchy's formula states, what it states is, if we know the stress tensor at any point, if we know this at any point, and if we cut one plane through that point, which has the outward normal vector like that, then the multiplication of these two basically gives us the traction vector at that point, traction vector component at that point. And traction vector component is nothing but Tn, and we will have three subscripts. This is along x, this is along y, this is along z.
Now, one thing I have pushed under the rug here is in this, the first x subscripts lie along the row, whereas when we discussed it earlier, it was lying along the column. That is, the first subscript x was along column 1 here, whereas here it is along the row. That is because Cauchy's stress formula actually is actually given as Tn. The vector is given by the transpose of the stress tensor. So in reality, this is actually the Cauchy's formula, which involves a transpose. However, since we have by equality of cross shears, sigma transpose is equal to sigma. So it is general convention that we generally drop the transpose there and write it this way. However, it needs to be kept in mind that one should not think something is inconsistent, because here the first subscript becomes xyz, whereas earlier when we actually said that we arrange the traction vectors in this order, the first column's first subscript was all x. That is because one is the transpose of the other, but by equality of cross shears, both come out to be the same. So going forward in our discussions, we may or may not use this transpose. I hope that does not cause a confusion. So far we have discussed the theory behind the Cauchy's formula. Now let us see an application problem that was discussed in the live sessions.
Till now we have discussed so much of theory about stress vector and stress tensor and so on. Let us see how to actually apply this to some problem. So we have a rectangular bar that has dimension 150 by 40, having a thickness of 1 mm, that is subjected to a tensile load of 0.5 kilonewton as shown in the figure. Answer the following question is what is asked. So what have we been given? This force we have been given as, this force is given to be 0.5 kilonewton. Now from the diagram itself we can see that this has to be 150 mm. When they have given the longer dimension, this is 150 mm. So what we'll do, we will cut a section like this, and when we cut that body and look at that section, we will actually see a rectangle. This rectangle has a width of, this is 40 mm, and has a thickness of 1 mm as given in the question. I hope that is clear. So this is just a rectangular piece being pulled, and at this point P we have to answer something. At this point P, what they have done, they have cut a plane like that. At point P they have cut a plane like that, which has a normal n, which makes an angle 60° with the horizontal. So let us say that our basis is again x, y, and z is coming out of the plane of the paper. So let us deal with two dimension presently. So this is x, this is y. So n cap, how can this be represented? This makes an angle 60°. So n cap is nothing but cos 60 I cap plus sine 60 j cap, or n cap can be represented as cos 60 sine 60. So this is the n vector. So far so good. Now the first question asks, select the 2D tensorial representation of the stress tensor at point P. Now what I'll do is, I'll take this diagram. So we have a long rectangular strip, and then we have a point P, and this is applied with 0.5 kilonewton on either side. Now let me take that point P and blow it up like this. On this, in the x direction, is there any stress acting along this direction? There is no stress acting along this direction. Is there any shear acting? No. So there is no shear acting, but there is a stress acting along this direction. And what is the value of that stress? This is nothing but P by A. Where P is the load applied, sorry, F by A, let us say. F by A. So this is the actual state of stress at that point. So this we can say F is 0.5 kilonewton divided by, what is the cross sectional area? Cross sectional area is the area of this rectangle, which is nothing but 40 into 1. So we have it as 40 into 1, which is nothing but by 40. So this is 12.5 MPa. Now when we take our basis like this, how will we represent the stress tensor now? It will be nothing but sigma xx, tau xy, and sigma yy. So our stress tensor becomes, in the x direction there is no force acting, there is no stress acting, so this becomes 0. In the y direction we have 12.5 MPa acting, so that comes here. There is no shear acting anywhere, so this happens to be my stress tensor at that point. I hope that is clear. So stress at point P is represented by this stress tensor. So let us see which of the option matches. We have this option D matching. So far so good. So this is MPa. Now the next question asks, magnitude of the component Txn in MPa of the traction vector. This is nothing but the stress vector on a plane if normal to the plane is oriented at 60 degree to the x-axis. So that is what was given. So we know that traction at any plane is nothing but the stress tensor into the normal to that plane. Now we have already found out the normal to that plane here, which is cos 60 sin 60, cos 60 I cap plus sin 60 j cap. So it is easy to find out what is the magnitude of, so on the plane at point P with normal at 60 degrees to x-axis, we have the normal as cos 60 sin 60. We have the stress tensor at point P as 0, 0, 12.5, which we calculated as the first question. So the traction vector, stress vector or traction vector is given by sigma n. So I have traction on the plane n along x, traction on the plane n along y. It is given by 0, 12.5 into cos 60 sine 60. So let us multiply this out. What do we get? So we get 0 and then we get 12.5 sine 60. So what does this mean? At that point P, let us say that this is the point P and we had cut a plane like this. And our plane's normal was n cap. Now we got the traction vector there as 0 and 12.5 sine 60. Let me replace 12.5 sine 60 by its value. Sine 60 is nothing but 10.83. Okay, so I'll just write 12.83 here, 10.83 here. So this means on this plane, the traction vector has components 0 and 10.83 MPa. So along x it is 0, along y it is 10.83, which means the traction vector is something like that. This is the traction vector or the stress vector which has a magnitude of 10.83. I hope that is clear. And this is 60 degrees. If this is perpendicular, then what does this angle become? This becomes 30 degree, although it doesn't look like that. Actually I should have drawn n more inclined, but I hope you get the idea. So this is how the stress state looks at on this plane at this point. Very well. So from here we know what is T n x, it is nothing but 0. T n y, it is nothing but 10.83 MPa. So this question asks magnitude of component T and x, it is 0. Magnitude of component T and y of the traction vector on the plane, if normal is this thing, it is 10.83 MPa. We just derived this. Now the next question is asking magnitude of the normal stress acting on this plane. From this diagram, can we find out what is the normal stress acting on this plane? It will be, I just have to project this traction vector to that, and this will be my normal stress. So what is that normal stress? On n. So geometrically we can see that normal stress, which is denoted by sigma n, is nothing but Tn cos 30 degree. Can we see that? I have a vector like that. I just have to find its horizontal projection. So it is nothing, it is making an angle 30 degree with the normal. So it is cos 30, which is nothing but 10.83 into cos 30, which comes out to be 9.38. Alright, now mathematically, how will we get this? Mathematically, how will we get this? We have traction vector. Basically, we have to dot it with our n. We have a vector, its projection on the normal is what we want. Geometrically, we have seen it is nothing but cos 30. So if we dot it with n, what will we get? The traction vector we got as 0 into 10.83 dot product with what is n? N is nothing but cos 60 sine 60. So what is the dot product? This is nothing but 0 cos 60 plus 10.83 sine 60. So this is nothing but 10.83 sine 60 comes out to be 9.38 again, which is same as what we got from geometry. Basically, this is also from geometry. I'm just telling you, given a traction vector and a normal vector, how can you find out the normal stress? Normal stress, if you want to go by geometry, you have to draw it. If you just want to find it out just using the vectors, you just have to take the dot product with that normal. So now that we have the normal stress as 9.38 MPa, let us answer this question. Magnitude of the normal stress acting on that plane is nothing but 9.38 MPa. Now this is asking what is the magnitude of the shear stress. Again, from geometry we can see that shear stress is nothing but this component. It is the component that is perpendicular to this. So for shear stress, we can do that quickly. Tau is nothing but Tn sine 60, which comes out to be, sorry, sine 30. So we want this side, so that is sine 30, which is nothing but half. So 10.83 by 2, 5.4, yeah, fine. 10.83 by 2 is 5.4. This is from the geometry. From mathematics, we know that traction vector is nothing but so the magnitude of the vector squared minus the normal stress squared. So how do we find the magnitude? We know that T n is nothing but 0 I cap plus 10.83 j cap, which I had just represented as a vector over here. So the same thing I have written in I and j. So how do we find the magnitude of this? Is nothing but 10.83 MPa. So therefore nothing but root over 10.83 minus 5.415 squared. Normal stress we got as 9.38. So this comes out to be 10.83 squared minus 9.38 squared. This is nothing but same 5.413 MPa. So the shear stress comes out to be 5.4 on this plane. Are there any questions at this point? If there are any questions, please feel free to ask. I hope it is clear. So what we are basically doing is, in a body, we took one point. and at that point we first wrote the stress tensor. Once we have written the stress tensor, by our previous discussion, we have captured all the traction vectors at that point along the infinite planes there are. So once we have done that, we have defined one plane which has a normal n, which is making an angle 60 degree with the x, and we are going about analyzing that plane. On that plane, what is the stress vector? What are the components of the stress vector? What is the normal stress? What is the shear stress? This is what we have seen so far. I hope that is clear. Okay.
So so far we saw a problem of applying the Cauchy's formula to a two-dimensional case. Let us also get conversant with how to apply this to three dimensions. Now, in the previous problem, we had to actually find out the stress tensor. But in this problem, we have been given the stress tensor, which is this, in three dimensions. And we have been asked to calculate the traction vector components and so on. Now, for this traction vector, it says the plane which is contained in the positive, the normal to the plane is contained in the positive octant, that is x, y, and z axis are all positive. So I'll just explain this. So basically, in the two-dimensional coordinate system, we have four quadrants, out of which the first quadrant, x and y, are positive if we are talking about the xy plane. Similarly, when we have things in three dimensions, basically this is the space will be cut in eight octants, eight cubes, out of which the first cube is x, y, and z are all positive. So this is the constraint that is given in the question. So basically x, y, and z. So what we are trying to say here is, if n is the vector represented by nx, ny, nz, nz, then all these three are positive is what is given. And it says that the outward normal has inclinations 48 degree and 61 degree with the x and y axis respectively. So let us see how to go about finding n. So our initial goal is to find n. So n has inclinations of 48 degree with x-axis and 61 degree, if I'm not mistaken, 61 degree with y-axis. So therefore, nx is nothing but cos 48. Ny is nothing but cos 61. Now we know that n is a unit vector. So therefore, nx squared plus ny squared plus nz squared is equal to 1. So from here, we can actually find out nz is nothing but root over 1 minus nx squared, which is cos squared 48 minus cos squared 61. So this is our nz. So let us calculate what these quantities are. So cos 48. So cos 48 is nothing but 0.669, and then cos 61 is 0.485. So 1 minus cos 48 squared. So 1 minus this. So this third quantity comes out to be 0.563. So we have got our normal vector to the plane of our interest. So this is our normal vector. Now let us see what the question is asking. What is the traction vector component along x direction, y direction, and z direction? So we have a recipe for this. I'll just take a copy of this. I'll put it here. So this is my sigma. Sigma is given by this. So using Cauchy's formula, I know that T, or rather let me use the capital one, T is given by this T is given by my matrix 56, 50, 32 into my traction vector into my normal vector, which is this. So, so if I were to multiply this out, I'll get Tnx, Tny, Tn, Z. So this comes out to be so so this comes out to be 79.74, 43.10, 91.27. So at once we have been able to find what the traction vector components are or the stress vector components are on this plane. So we have the answers here. So let us just copy and take them here. So this is our Tx, Ty and Tz. So far so good. The component of traction that is normal to this plane is what is asked. Now we saw that this is our traction vector. This is Tn. So on any plane, if this is the normal and if we have the traction vector like that, we know that the projection of this onto the normal is our normal stress. So the normal stress is given by Tn dotted with n. So I can do that here. So the normal stress is nothing but sigma n is Tn dot n, which gives me sigma n is the traction vector is here dotted with my normal vector. So this gives me, so this comes out to be 125.66 MPa. I hope no one has an issue with dot product. Basically, we are just multiplying the respective quantities out and then adding them. So that is what a dot product is. So our normal stress comes out to be 125.66. So let us write that here. So we have got this as 125.66 MPa. Now the traction vector that is tangential to the plane, we know that if this is normal, we know that if this is the normal component, then our tangential component would be like that. So we can find this out using the relation. We know that Tn, the magnitude square, is nothing but tau n squared plus sigma n squared, or tau n is nothing but root over this minus this. So let us see what the magnitude is. So the magnitude of any vector, if this is Tn, then the magnitude of Tn is nothing but Tn dotted with Tn. So I just have to take this. So for the shear stress, I have Tn dotted with Tn minus the square of this. So this is my tau n, which is root over this quantity. So let us see what that comes out to be. So the shear stress tau n is nothing but so this is root over 16545.77 minus 125.66 squared, or tau n comes out to be 16545.77 minus 125.66 squared. So this comes out to be 25.77 MPa. So we have got the shear stress as 25.77 MPa, which we can write it here, 25.77 MPa. Now the last question asks, determine the angle between the stress vector and the normal to the plane. So what are we looking at here? So we have the plane like that. We have the normal like this, and then we have the traction on that plane. So this angle is what is asked. So we know that this quantity is nothing but my normal stress, and this quantity is nothing but my shear stress. So from here it follows that tan theta is nothing but tau n by sigma n. So tan theta tau n, we got it as 25.77 by 125.66. So we have got this relation. So from here it follows that that angle is 25.77 by 1 comes out to be 11.58. comes out to be 11.59 degrees. So this angle is 11.59 degrees. So far we have seen how to apply Cauchy's stress formula to find out the stress vector on any arbitrary plane in 2 dimensions and 3 dimensions, provided we have the stress tensor with us. Now it turns out that stress tensor will not always be given in a coordinate system that we want. So we may have to do transformations similar to vector transformations, where we transform one vector in one coordinate system to another coordinate system. There is also a procedure to be followed when we transform second order tensors such as stress tensor and strain tensor, as we will see. So the next discussion from the session will be on how we transform second order tensors.
Let this be x, let this be y. So I have y. Now I have x prime, and let us say this is y prime. This is y prime. Now x prime, a vector along x prime, I can represent, let this be theta. Let the angle that it makes with x be theta. So this can be represented as cos theta x plus sin theta y. Similarly, y prime can be represented as minus sin theta x plus cos theta y. This is simple vector transformation. Now what I'll do, I'll just bundle this up. I will write it like this: x prime, y prime. I can write it as cos theta. I'm just collating the coefficients in a matrix form. There is a reason why I'm doing this, which I will explain. So this is cos theta into x, y. Now you can simply multiply this and see that you will get the same answers as we got before.
Yeah.
So what this means is that this is a matrix basically that rotates a vector in the xy plane to a new coordinate system x prime y prime. So any vector that I have in the xy represented in the xy coordinate system, if I multiply by this matrix, it will give me the components of that same vector in the x prime y prime coordinate system. So far so good. So this is one information that we have. All right. So what I'll do now is, for the sake of this example, let me take Cauchy's stress formula. Which basically states that T along some n is basically sigma into n. Mr. Jayakrishnan, could you mute the microphone?
Sorry,
Yeah,
apologies.
yeah. Okay. So now what we can do is, in the xy direction, so T, let us taking the x plane. I'll take one, I'll take a body, and at that point the normal that I have cut, it is along x prime, and it has a traction vector like that, let us say. So how do we represent the traction vector? As t, and we have to represent the normal vector along that. So t x prime is nothing but x prime t y, t x prime x, t x prime y. Let us say that the stress tensor at this point is represented as T sigma xx, sigma xy, sigma yy, and sigma xy again, and sigma yy. Okay, so I have the stress tensor here. Now I want to find out that this traction Tx prime. So Tx prime is nothing but along x, Tx prime along y. I just have to multiply this by the normal. Normal of x prime is nothing but cos theta and sin theta. We just saw. X prime can be represented as cos theta x plus sin theta y. So I just have to put that here. Cos theta sin theta. So this much I have got. Now the issue is this is represented in the xy coordinate system. I need to represent in the x prime y prime coordinate system. So what I'll do, I'll just transform this. So we saw that how a vector transforms. A vector transforms like this. So given one vector, if I multiply it by this matrix, I will get the same vector in the new coordinate system. So following this, if I take this vector, which is Tx prime, y prime, and I want to transform it to the primed coordinates, I just need to take this matrix and multiply it by its original vector. What is the original vector? It is this entire thing. Once I do that, I get the this is basically the traction vector on the xy plane in the x prime y prime coordinate system itself. Similarly, what I do now, what have we got? Now we have got or I should say the stress vector x prime plane represented in the x prime y prime coordinate system. I have this on the x prime plane. There is a traction vector which I have represented in that x prime y prime coordinate system, and I have got this expression. Similarly, I would want the same thing but in the y prime plane. If I take the y, now let us take the y prime plane. So what is traction in y prime? Y prime, y prime. Now I will represent it as x, y as we usually do. So this will be nothing but sigma xx, sigma xy, sigma xy, sigma yy into the direction cosines of the y prime plane. From here we saw direction cosine of the y prime plane is minus sine theta cos theta. So I just need to write minus sine theta and cos theta. Again, this is represented in the xy coordinate system. I again need to transfer it to the x prime y prime coordinate system. So what do I do? Taking the same logic that we have this matrix which actually transforms it. So what I'll do, I'll take this, I'll put the prime coordinates, which is nothing but that matrix, this matrix, into that original vector. The original vector is this. So what we have got now is, we have got two planes, x prime and y prime. We have two planes, x prime and y prime, and we have stress vectors represented on those two planes. In the x prime, y prime coordinate system. So if I club this together, let me club this together and show what happens. Presently I have one equation like this, which is telling me what is the traction vector on the x plane in the x prime y prime coordinate system. Similarly, I have another expression like this, which is telling me what is the traction in the y prime plane, same again in the x prime y prime coordinate system. So there is a convenient way to club all this into one matrix. What I'll do, I'll just put this here, and I will put this here. Second one, I'll put it here. Fine. And since we are reserving curly brackets for vectors, I'll put this like this. What I have done, I have just taken the left hand side of the first two equations and I put it side by side. So this can be represented. I'll just copy this. This is nothing but is equal to this into the stress vector into some matrix, which is again the right hand side. I will just put it side by side. So sine cos, I have put it here. This I have just brought it here. So this is how the transformation comes about.
So we can rewrite this as, so we know this is nothing but sigma x prime, and this we know it is tau x prime, y prime, and then we have sigma y prime is given by this expression. Is given by this expression. In fact, instead of sigma xy, let me consistently use tau xy so that there is no confusion at a later stage. So this is the stress transformation equation in the matrix form, which we'll be using time and again. So just to see how the expanded form looks, I'll just cross multiply this, open up the brackets and cross multiply this. From here, if I were to write this component and these components separately, what I will essentially get is sigma x prime is nothing but sigma xx cos squared theta plus sigma yy sine square theta plus tau xy sine 2 theta. Similarly, tau x prime y prime will come out to be minus sigma xx sine theta cos theta plus sigma yy sine theta cos theta plus tau xy cos 2 theta. Now I can simply substitute. This is sine squared theta. It is 1 minus theta. So when I substitute this, I'll get sigma x prime as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. Similarly, I'll get tau x prime y prime as minus of this quantity into this plus this into this. So this is my stress transformation equation as such, not in a matrix form but opened out. So these are my stress transformation equations. Now let us apply this to a problem and see how it actually works. So let us say that we have a stress state like that, and let us say that we rotate 50 degrees counterclockwise. So according to our convention, theta is plus 50 degrees because we take counterclockwise rotations to be positive. So our aim is to find out what is the normal stress and what is the shear stress on that plane. So let us see how to go about doing that. So here we can see, so sigma x is 50 MPa, sigma y is 30 MPa, and tau xy is plus 20 MPa because it is pointed towards the positive direction on the positive phase. So now after rotating by 50 degrees, so we'll have sigma x prime as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. Similarly, we'll have tau x prime y prime as minus of this quantity into this plus this into this. So what does that come out to be? We will have sigma x prime as 50 plus 30 by 2 plus 50 minus 30 by 2 into cos 100 plus 20 sin 100. So this comes out to be 57.96. Similarly, tau x prime y prime comes out to be minus 13.5 32 MPa. So this is our normal and shear stress on a plane that is rotated by 50 degrees. So now it begs the question, why are we doing it this way? We already know that when the normal to that plane is oriented at 50 degrees, we already have a recipe to find out what the normal and shear stresses are using the Cauchy's formula. So let us see why actually we need this instead. I'll just solving this using Cauchy's formula. So our aim is to find out sigma x prime and tau x prime y prime on a plane whose normal is cos 50 and sin 50. So we know that sigma, the stress tensor for this stress state, the stress tensor is 50, 20, 20, and 30. We can clearly see that. So therefore, the traction vector on this plane is nothing but this into this, and it follows that sigma n there is nothing but my traction vector dotted with n cap, and tau in n is nothing but my traction dotted with itself minus sigma n the whole squared. So this we have already done for two problems earlier. So why could we not do the same thing? Why did we need to derive the stress transformation equations and go through this circuitous route of finding out sigma x prime and tau x prime y prime? So if I were to multiply this out, this comes out to be 50 cos 50 plus 20 sin 50, which comes out to be 47.46, and 20 cos 50 into 30 sin 50 comes out to be 35.84. So therefore, sigma n is nothing but this dotted with this, which comes out to be 57.96 MPa. And what were we getting from the stress transformation equations? We can clearly see here we were getting the same value. So that to that end it is consistent, no problem. Now coming to the shear stress, it is nothing but this dotted with itself minus square of this. So tau n comes out to be 47 dotted with this. This will come out to be 13.33 MPa. And what did we get from the stress transformation equation? We got minus 13.32. So this is one of the drawbacks in using the Cauchy's formula, because since we are taking the square root, even the negative shear stress or positive shear stress both will square up to the same quantity. So hence the sign is lost. So the sign of the stress is lost. We don't have that information if we were to solve it using the Cauchy's formula. So one of the need is, if we want to obtain the sign also, we need to go for these stress transformation equations in order to actually obtain the results with signs. So far, so good. So for this example, what we have seen, we derived the stress transformation equations, opened them out, wrote it in the long form, and we saw for a simple problem, we saw how it is to be applied, and we were able to find out what was the normal and shear stress on a plane that is rotated by 50 degrees for this problem. Now this begs the question again, is there an easier way to do this? So it turns out that there is. Perhaps this can be represented as a curve, and we can go about doing our manipulations there, the rotations there, which is what is the idea behind the Mohr's circle. So let us see that now. So these are the stress transformation equations as we have it. So what I'll do, I'll move them around a bit. Let me square it plus this squared. So on the right side, what is left? These two quantities are left for the first equation, and for the second equation, these two quantities are left. So we can see that this squared plus this squared basically drops the negative sign. Cos square 2 theta plus sin square 2 theta is 1. So this just leaves us with this quantity on the right side, the whole square, plus again when we square and add these two, we get only tau xy squared remaining. So this equation we have been able to get by simple manipulation. So this is of the form. So this is of this form, which we can clearly see. It is the equation of a circle with a center at c comma 0 and radius equal to r. So this is nothing but the equation. So given this equation, one might think that we can simply plot this circle like any other curve that we do. But in the context of our stress transformation, or rather tensorial transformation, there is something to be kept in mind here. There is one issue here. So let us see what that is. There is an issue in plotting the Mohr's circle, just as it was any other curve. So it is better that we try to understand this using the same example that we have already solved. So we took this stress block here, and using the stress transformation equations, we know what sigma x, sigma y and tau xy were, and we have already derived what the stress on a plane that is 50 degrees rotated is. So we know that sigma x prime y prime is 57 there, and tau x prime y prime is minus 13.32. So we can actually solve the same problem using the Mohr circle in order to understand what the issue is in plotting the Mohr circle just like any other curve, and why we need to follow certain conventions. So let me keep this value here, and let me bring out the graph sheet in order for me to plot. Let me take the rough scale. So this 1 unit, let this be 10 MPa for the sake of plotting. Now how will we go about plotting any general curve? We have one axis like that, the other axis like this.
In this context,
This happens to be our sigma x prime axis, and this happens to be our tau x prime y prime axis. So what is the center of this Mohr circle? For this stress state,
what is the center of the Mohr circle?
we know that the coordinate of the center is sigma x plus.
Sigma y by 2.
So the center is nothing but sigma x plus sigma y by 2, which is 40 MPa, and the radius is nothing but the square root of this quantity. So sigma x minus sigma y by 2 whole squared. So radius is nothing but 50 minus 30, 20 by 2 the whole squared plus 20 squared root over. So the radius comes out to be 10 squared plus 20 squared root of 500, so which is around 22.36. So we have the center, we have the radius of a circle. How do we plot a general circle? The x-axis is there, while the y-axis is there, horizontal and vertical. So let us first find out where the center lies. So this is 10, 20, 30. So this is where the center of the circle is. And the radius is 22 something. So let us take this to be the circle. So the circle comes out to be this way, where the center is 40, 0 and the radius is 22.36 MPa. Now let us plot the x-plane. On the x-plane, if we observe this, on the x-plane, we have a normal stress of positive 50 and a shear stress of positive 20. So what do we generally do in plotting any curve? So the positive x goes to the right, the positive y goes on top. So this is 50 and this is 20. So this point happens to be my x-plane. So this point happens to be my x-plane. So let me draw a line connecting this. So what is this angle? This angle is nothing but 20 by 10. This is 20, this is 10. So this is nothing but tan inverse of 2, which is around 63.45 degrees. So this is 63.4 degrees. If this is 63 degrees, it implies that this angle is 116.56 degrees. So this is 116.5 degrees. Very well. So our idea is when we rotate by anti-clockwise 50 degrees, we want to find out what is sigma x prime and tau x prime y prime on that plane. So naturally, when we rotate it in the physical plane by 50 degrees, in the Mohr circle, we need to rotate it by twice that amount. So since we have rotated there anti-clockwise, what happens if we rotate here anti-clockwise? So we can see that this angle is 116. So when I rotate it anti-clockwise, I'll come somewhere around here when I have to reach 100. I hope that is clear. So initially I was here. Now I have to rotate 100 degrees. Since in the physical plane I rotated in the anti-clockwise direction, if I rotate the same manner in the anti-clockwise direction, I will come somewhere over here. So this angle is nothing but our 116 minus 100. Let this be the line joining that. So this angle is nothing but 116 minus 100, which is 16.5 degrees. And if we want to determine the shear stress, is this much. The normal stress will be the perpendicular distance here. So here it turns out that the shear stress is coming out to be something positive, whereas we clearly saw for this question that the shear stress after rotating anti-clockwise by 50 degrees was coming out to be negative. This is the issue with plotting Mohr's circle, just like any other curve. So basically there are two conventions to plot the Mohr's circle. Convention 1 is positive normal stress towards the right, positive shear stress downwards, downwards, and anti-clockwise rotations in physical plane need same anti-clockwise rotations in circle. Convention 2. The second convention is that we have again the normal stress pointing to the right. This remains the same, but the positive shear points upwards. When the positive shear points upwards, then anti-clockwise rotations in the physical plane need clockwise rotations in the circle. So let me just explain what this is. What we are trying to say, in this case, we have been following the second convention basically for the axis, because we have plotted positive x prime towards the right. We have plotted positive tau x prime y prime upwards. In such a case, when we do these two, then when we rotate anti-clockwise in the physical plane, we have to rotate clockwise by twice that angle in the Mohr's circle in order to get to the correct answer. So what this means is, I went like that. Instead, I should have gone this way by 100 degrees. So if this is 60, then I go another 40. I get to this point where I can clearly see that my shear stress now is actually negative. So I hope these 2 points are clear. So these are the 2 conventions we generally follow. What is followed in the lecture is the axis, although it is shown like this, we will still plot positive shear downwards and negative shear upwards. So this is basically negative shear. This is what is being followed in the lecture. So this will become clear if we solve some problems. So we will essentially be following this convention. We will follow convention 1 in order to solve our problem. So let us look at some problems from the Mohr circle. I have actually collated some interesting problems. These have basically all the types of problems contained, so that we become confident with solving the Mohr circle. So let us look at these problems one by one. So in the interest of time, I have selected a couple of problems and I have pre-filled some of the data.
so that we can just look at how it is to be plotted. And I encourage the viewers to work these out on their own once so that it becomes clear. So the same problem, we have the stress cube, we have the coordinate system x and y as that. So this is the x plane, this is the y plane. So we have sigma x is 50, sigma y is 30, and on the positive phase, shear is applied in the positive direction. So this is plus 20 essentially. So the shear here is positive. So how do we go about plotting the Mohr circle? First is we have to find out the center. Center is nothing but sigma x plus sigma y by 2, which is coming out to be 40. So for the sake of all the problems, I will be following this grid. In essence, we need not follow everything to the scale, but just to make things clear and to have a visual appreciation, I have used the grid here. It is up to the discretion of the viewers whether they want to use this or not. In any case, here in the grid, 1 unit is 10 MPa I have taken. That is the scale I'll be following throughout all the problems. So the center is at 40. So this is 10, 20, 30. So this is the center. Now I have to plot the x-plane. So I know that sigma x on the x-plane, sigma x is plus 50 and tau is plus 20. So I can see here that the positive tau axis is pointing downwards because we are following this convention. Convention 1, this is consistently to be followed throughout the course. So we have the positive normal stress pointing to the right, positive shear pointing downwards. Once we follow this, if we make an anti-clockwise rotation in the physical plane, it will translate to the same kind of rotation in the circle as well. So this is 50, this is 20. So let us plot the x-plane. So I have 50 and then I have to go down by 20. So this is my x-plane. This is my x-plane. So once this is plotted, it is easy for me to draw the circle. However, I can also locate the y-plane, which will be diametrically opposite. So it will essentially be this point. So it will essentially be this point. Now I can draw the circle like that, which passes through these 2 points comfortably. So this is my Morse circle for this problem. This happens to be the x-plane and this is the y-plane. So let us look at the next problem. Here we have everything to be the same, that is positive normal stress on the x, positive normal stress on the y, but on the positive x plane we have shear stress acting downward. So this is essentially negative. Tau xy here is negative. I hope you can see why that is. On the positive face it points in the negative direction, so tau xy is negative. So the center as usual is at 55. So let me plot the center. So 2, 3, 4, 5. So center is at 55. So far so good. Sigma x at 70. So 55, 60, 70. So this is the sigma x line for the x plane. And then I have negative 30. So negative goes this way. So this is essentially my x plane. So I can mark the point over there. This is my x plane. Which means diametrically opposite, this will be my y plane. And then I can draw the circle passing through these 2 points with the center like that. Something like that. So this is the Mohr circle for this problem. So now if we have a question that we rotate by positive 10 degrees,
about the x-axis. So what do we have to do in order to find that? So we have this as the x-plane. So we essentially have to rotate by 2 theta, by 20 degrees we will have to rotate. This will be our new point of interest. So I hope that is clear. Similarly, let us look at this problem. Here we have the center at minus 20. So we have this at minus 20 where sigma x is negative, sigma y is still positive, and tau is also negative. So negative tau will go upwards. So we have minus 60 as the normal stress, 20, 30, 60, and this is, so we have the x plane over here. So it is quite big that way. And then the y plane is plus 20, and then this will go down like that. So this is my y plane. So my Mohr circle is a bigger one this time. It is something like that. So I hope you're able to appreciate how to plot the Mohr circle. Let us look at one more example where there is no sigma y this time. There is only sigma x, which is positive. And then we have shear stress. On the positive face, it points upwards. So the shear stress is positive and of the magnitude 30 MPa. So the center of the Mohr circle is at 30. So let us plot the center. Center is over here. And then we have, so this is 60, comma. So the x plane has the ordinate 60, comma, rather plus 60, comma, plus 30. So plus 60 goes here and plus 30 comes down like this. So this is the x plane. And then for the y plane, it is 0. Normal stress is 0 and this is 30. So this is the y plane. So my Mohr circle is like that, passing through these points, these 2 points. So this is my Mohr circle for this problem. Let us look at this where there is no normal stress essentially. So the center is at the origin. So we have the center at the origin and the x plane. The x plane has no normal stress. So the x axis will be 0. That is the horizontal value is 0. And for as for the vertical value on the positive x plane, our shear points downward. So this is essentially negative shear. Negative, as we can see clearly, has to be plotted upwards consistently. That is what we have been doing. So this is minus 40. So this is 10, 20, 30, and 40. So this is my x plane. Similarly, y plane is diametrically opposite 10, 20, 30, 40. So this has come over the, I'll just move this a little bit here. So this is my Mohr circle for this problem. Passes through these 2 points. And this is the y plane. Y plane. So let us look at one last problem where there is shear absent this time. We have only normal stresses. So when there are only normal stresses, let us see what to do. Our center is at 55. So let me plot the center. This is 50. So this is 55. And then I have the x plane. On the x plane, normal is positive 70. There is no shear. So the vertical axis value is 0. The horizontal axis value is over here. So I have the x plane over here. So this is my x plane. Similarly, my y plane will be at 40. So this is 55. So this will be my y plane. So this is essentially my y plane. And I have a Mohr circle like that. Like that. So in this case, we know that when there are no shear stresses present, the normal stresses basically intersect the axis here, and it can be seen from this circle. So at this point, there is no stress that can be more than this. Essentially, all other normal stresses are less than 70. So 70 happens to be the maximum principal stress in this plane, and there is nothing below this in this plane. So 40 happens to be my minimum principal stress for this plane. So this is what principal stresses are. This will be discussed in more detail in the classes to come. But in the interest of time, I'm just confining my attention to the Morse circle. So I hope with all these examples that I've covered all the types of combinations, basically positive shear stress, negative shear stress, how normal stresses vary, positive, negative, no normal stress, and only normal stresses and no shear stresses. So for all those combinations, we have drawn the Mohr circle. So I hope that the conventions are clear now and the viewers will be able to do it confidently. So in this context, let us look at this problem and quickly wrap it up. With reference to the Mohr circle drawn below, answer the following sub questions. The normal stress is plotted along A or B is the question. So we know that the normal stress is plotted along A. This is my normal stress. Essentially, this is nothing but sigma x prime x prime. So this is plotted along A. The shear stress is plotted along A or B. We know that shear stress is plotted along B. And as per our convention, this will be my positive tau x prime y prime. And pointing upwards, that will be negative. So that we have rotations in the physical plane match with rotations in the Mohr circle, which we have discussed in much detail in the earlier problems. Point representing the location of maximum shear stress is which of the following? Now, this is the shear stress axis. So, whichever line we draw that subtends the maximum intercept is my point of maximum shear. So, E basically subtends the radius. There can be nothing more than the radius of the circle that it can have an intercept. So, that is why E is our correct answer. So, I hope you are able to see that. So, this is E. Following the convention developed in the lectures, as we have just discussed in the previous questions, the sign of the shear stress at point G of the Mohr circle is what? The sign of the shear stress at point G. So we can clearly see in all our questions the conventions that we have followed that positive shear stress points downward. So at point G, the shear stress is negative. Following the convention, what is the shear stress at F? So F is pointing down from the axis where the shear stress is positive, as we have seen umpteen number of times now. So I hope the viewers find no problem in identifying that this is positive. The angular difference between points F and G on the physical plane is what? Points F and G. So if we see here, points F and G in the Mohr circle are 180 degrees apart. So in the physical plane, it will be 180 by 2, that is 90 degrees apart. So essentially, F and G represent perpendicular planes, as we saw here. Always X and Y plane were 180 degrees apart on the Mohr circle, and in physical reality, we know in the physical plane, it is always 90 degrees apart. So this is 90 degrees apart. So this question asks, for getting the principal directions associated with the major principal stress, one has to measure dash from the x plane to the point indicating the major principal stress direction on the Mohr circle and report what times. So essentially what this question is asking is, let us take this Mohr circle as the example. So now that we have the explain over here, in order for me to arrive at the maximum principal stress, I know that maximum principal stress for this problem is over here. This is my point of maximum principal stress. So in order to arrive at that, I have to measure this angle. So what this means is, if this is 2 theta p, I have to measure this angle, and theta p will essentially be the rotation I have to impart to this stress element. This has to be rotated by theta p in order for me to arrive at the maximum principal plane, which will be carrying the maximum principal stress, of course. So I hope that is clear. So essentially we need to measure it in the counterclockwise direction and report half the value of that. I take it that it is now clear. So let us look at this question. For a three-dimensional model subjected to stress field, there will be a maximum of how many principal planes at a point corresponding to the principal stresses. So we saw that for 2 dimensions, there are 2 principal planes. Essentially, for 3 dimensions, there will be 3 principal planes. There will be 3 stresses. And we will see how the Mohr circle is plotted in 3 dimensions in the coming session when it will be discussed. So let us look at this last question quickly. Answer true or false. Option A says stress tensor gives the information about the totality of stress vectors on all the possible infinite planes passing through the point in a body. We saw that given a stress tensor and any normal stress, we can find out the traction at that point. So stress tensor basically contains all the stress vectors within it, and we expose those stress vectors by giving it a normal. So this is true. The stress tensor is non-symmetric due to equality of cross shears. We have clearly seen that this is not the case. It is symmetric. Each point on the Mohr circle represents a specific plane, as we have seen in excruciating detail now by plotting so many Mohr circles, that each point does represent a specific plane. There will be some amount of normal stress on maximum shear stress plane in general, except for the pure shear cases. So do we have any pure shear cases that we discussed? Here there was no shear stress. Here there was only shear stress. So this is what is known as the pure shear state. And in this case, we see that this happens to be the maximum shear stress plane. This is where the shear stress is peaking. And here the normal stress is essentially zero. Except for this, we saw that everywhere, in all the cases we saw, except for that pure shear case, except for this pure shear case, we saw that everywhere our Mohr circle is either to the left or to the right, which implies as soon as it is to the left or to the right, wherever we have the maximum principal plane, maximum shear stress plane, there will be some non-zero normal stress acting on that. And actually that will happen to be the ordinate of the center, which will be nothing but the average shear stress. So the normal stress acting on the plane of maximum shear stress is actually this much, always. So I hope you are able to appreciate that. So this is true. This is true. So TFTT is our answer. So I apologize for pulling this session a bit longer because I had to explain certain things in detail as to why the conventions have to be followed. So I hope that viewers are able to appreciate that and will be able to solve the assignment problems easily, which has questions on stress transformations, equilibrium equations, and so on. Thank you.